Hello. We will get started in about 30 seconds. All right. Welcome, folks. Let's get started. So, welcome to the 25th day of remote learning. Today's joke, I wasn't sure whether I was going to tell it. And the reason is that it is a joke you probably won't understand. You'll have to tell it to your parents and get them to explain it to you. But because I'm as old as your parents, I think it's a pretty funny joke. So the joke is two rabbit ears got married. How was the ceremony? It was nice, but the reception was amazing. So today we're going to look at solving linear inequalities. There are two handouts in the classroom. We're going to be working through the first one, 4.09.h, not .h3. And we are looking at linear inequalities. I'm just going to make sure that I get onto the screen here. So linear inequalities. So what do we mean by that? Well, it's any situation where we have an inequality that compares a linear function to a constant or a linear function. So what does that mean in practice? That means that we might have something like 2x minus 7. That is a linear function or expression. And we are going to compare it to, in this case, a constant 3. And so compare means greater than, less than, or either of those with the equal to possibility. If we were comparing a linear function to another linear function, we might have something like 3x plus 2 less than 2x plus 12. All right. I wish we could get just a little clearer with the focus here. There we go. Okay. So let's take a look at how we solve each of these. So there is a lot of similarity to the work that we've done on solving linear equation. And as we go through and solve other types of inequalities, we'll see again that the work that we've done on equations is really helpful, but we need to be a little bit careful. So let's look at this one here, 2x minus 7. I can add 7 on both sides. And of course, when we're solving linear equations, we usually just do this in our heads, but we're going to be really clear about each step here. So then negative 7 plus 7 is 0. So we end up with just 2x. And then on the other side, 3 plus 7 is 10. Now we divide both sides by 2. And we end up with x greater than or equal to 5. All right. For this one here, we have negative 3x plus 2 less than or equal to 2x plus 12. So if we add 3x on both sides, and then we subtract 12. So negative 3x plus 3x is 0. 2 is all that's left. Going to subtract 12 on both sides now. 2x plus 3x is 5x, plus 12 stays, and we have to subtract 12 on this side as well. So 2 minus 12 is negative 10, less than 5x. 12 minus 12 is 0. There we go. And now we can divide by 5, divide by 5. 5 divided by 5 is 1. 1 times x is x. And on this side, we get negative 2. And usually we'll write these x greater than negative 2. Just like if we had an equality here, we would switch the things. The thing we need to be careful about now is because a less than or greater than sign has a direction to it, if we swap the sides, swap the x and the negative 2 in this case, we also have to change the direction of the inequality. So here it was less than, it has become greater than. Negative 2 is less than x, x is greater than negative 2 are the same statement. Okay. So you're probably looking at that going, all right, so Mr. Island, you said that this was going to be a little bit more complicated than solving a linear equation, but so far it looks exactly like solving a linear equation. So we're going to break it down. There's a little table there in the document, and we're going to see which operations that we do to both sides maintain the inequality. And so by that, I mean for here, for example, we added 7 to both sides. Here we divided by 2 on both sides. Here we added 3x to both sides. Here we subtracted 12 on both sides. Here we divided by 5 on both sides. So we've done various operations on both sides of an equation. And we just want to check, of an inequality. And we want to check whether doing the same operation to both sides of an inequality maintains the inequality or not. We know that if it's an equal sign, doing the same thing on both sides maintains equality. In this case, we're checking it for inequality. So first thing is add to both sides. So we know, for example, 3 is less than 9. If I add 5, for example, on both sides, I get 8 is less than 14, and that is still true. So true. What about subtraction? So if I subtract from both sides, 3 minus 1 less than, actually, let's start with 3 less than 9. 3 minus 1 less than 9 minus 1 gets us 2 less than 8. That is still true. What about multiplication? Well, we have 3 less than 9. We can do 3 times 4, let's say, less than 9 times 4. We get 12 is less than 36. That is still true. What about division? Three is less than 9. Well, let's say we divide by 3, because that's going to work out nicely here. 3 divided by 3 is 1. 9 divided by 3 is 3. True. We need to be a little bit careful, though. Here I've multiplied by a positive. And here I've divided by a positive. What happens if we do multiplication and division by a negative? So let me move this up, get some extra space here. So multiply by negative. Well, let's start with 3 less than 9. What if we multiply by negative 2 on both sides? We get negative 6 less than negative 18. That is no longer true. Negative 6 is greater than negative 18. You might recall that if we have, let me find a good spot to put it here. If we have a number line numbers that are greater than are on the right of numbers that they are greater than. So we have 0, we had 3, somewhere up here was 9. 9 is greater than 3 because it is to the right of it on the number line. If we go down into the negatives, -1, -2, -3, -4, -5, -6, -7, -8, count down all the way to -18, we can see that -18 is to the left of -6. That means -6 is greater than -18. But here we find that the inequality is telling us the opposite. So this is false. If we divide by a negative, let's take a look here. So we have 3 less than 9, and maybe we divide by -1. So 3 divided by -1 less than 9 divided by -1, -3 less than -9. And once again, we find that this is false. -3 is going to be to the right of -9, so it should be greater than -9. So what do we get out of all of this? Well, when we multiply or divide by a negative, we need to flip the inequality. So you can remember this rule, but I think it's a little bit easier to understand what's happening in terms of, like, I almost think of it as transformations. When you multiply numbers by the same thing, you're going to be stretching or compressing them. So if I take 3 and I multiply it by 2, I'm stretching it out to 6. And that kind of makes sense. Like we know that multiplying, oops, sorry, you can't see that. So if I take 3 and I multiply it by 2, I'm doubling its distance from 0. I'm stretching it by a factor of 2. And we know this when we look at transformations of functions. When we have a vertical transformation by a factor of 2, it stretches everything to be twice as far away from the x-axis or twice as far away from the value of 0 on the y-axis as it originally was. So the 3 gets doubled out to 6. The 9 gets doubled out to 18. So we've had this stretch happen by 2. Well, stretching things doesn't change which one is closer to 0, right? 3 gets stretched out to 6, 9 gets stretched out to 18. There's not going to be any change in which one is closer to 0. But if we multiply by -2, we've not only done this stretch, we've also done a reflection because it's negative. And we're reflecting everything to the other side of 0. So the 3 is getting stretched and reflected over here to -6. The 9 is getting stretched out to 18 and reflected over here to -18. It still maintains that things are farther from 0. So the 9 was farther from 0 than the 3. 9 gets moved to 18, which is farther from 0 than -6. So anytime we do a stretch or a compression, we maintain whichever of the two numbers was closest to 0 stays closest to 0. If that's only happening with a stretch, there's no reflection, then we're maintaining greater than or less than. But as soon as we get a reflection, that's going to swap which one is above and which one is below, just like a reflection does for functions. And so that's one way of thinking about why, when you multiply by a negative, you are having to change the direction of the sign, because you've kind of reflected everything around zero, which means you've swapped which one is to the right. And since you've swapped them, you need to change the sign to keep it true. All right, so I'll pause there. Let me know if you have questions, or give me a 1 in the chat if that is making sense to you. Okay, I'm not seeing much response. I will keep an eye out for questions. Let me know if there is anything you're wondering about this. So we're going to keep moving through the handout. There's a phrase: when solving linear inequalities, you are asked to find the blank interval that makes the inequality true. The word to go in the blank there is real, and that just means real numbers. And I think you were most likely assuming that we were solving with real numbers. So let's take a look at solving some of these, and we'll also talk about expressing the solutions in different ways, and we'll talk about the graphical interpretation of this solving. So let's flip it over. 3x minus 1 less than 8. So this is the first example there. We're going to go through, add 1 to both sides. We know that adding and subtracting, and it actually turns out for adding and subtracting, it doesn't matter whether they're positive or negative numbers, that maintains inequality. So we have 9 greater than 3x, or 3x is less than 9. We're dividing by 3. Since it's a positive number, we don't have to flip the inequality, and we can just say x is less than 3. So some different ways to express this. Well, we have set notation. X belongs to the real numbers such that x is less than 3. So that is set notation. We also have interval notation. And so this is similar to what we talked about way back when we were in the classroom. So we're stretching from negative infinity to 3. And you'll recall we use round brackets when the endpoint is not part of the interval. So numbers that are less than 3 don't include 3. So we have a rounded bracket to show that 3 is not included. Negative infinity is not a real number, so it's not included in this interval. It just shows us that we keep going forever in that direction. So there's an interval notation way of writing it. And the final way that we have is to express it on a number line. I'm not going to draw the whole number line in here, but I'll put 0 and I'll put 3. We'll use an empty circle, not a filled in circle here. That indicates that 3 itself is not part of the solution set. We are talking strictly less than 3. We're not including equal to 3. And then we just draw an arrow, and we put an arrowhead showing that it continues forever in that direction. All right. Whoa. My apologies. So let me go through that. So we have 3x minus 1 less than 8. We do our regular linear solving. We don't need to flip the sign because we've divided by 3, and 3 is a positive number. If we were dividing by negative 3, then we would have to flip the sign. And so we have 3 ways to express the solution: as a set, the set of all x less than 3 that are real numbers; as an interval; or on a number line. Empty circle and our number line showing it there. All right. So hopefully that's making sense, these ways to show it. One other interpretation that we can give for this is a graphical interpretation. And it's useful to think about how this would look if we graphed what we have on both sides of the equation. So I'll open up my Chromebook here and show you that. Desmos calculator. Okay. So Desmos, we had 3x minus 1, 3x minus 1, and we had on the other side of the inequality 8. And so we'll do them separately. We're not going to type it as an inequality in here. And I'm just going to scroll down so that we can see this. I might need to go y equals in front of the 8. And I'll put it here as well for consistency. So it might be a little hard to see. I'm going to try and change the color. How do I change the color? Oh, there we go. All right. So here's the line 3x minus 1. Here's the line y equals 8. The inequality is asking us for what values is 3x minus 1 less than 8. In other words, where is this line less than or below this line? And we can see if we follow the spot where they cross downwards, they cross at 3. And anywhere where x is less than 3, we have 3x minus 1 being less than 8. And so that matches up with the algebraic solving that we did. This is one way to picture in your head or on a Desmos screen what's happening. And it's also a really easy way to check your work. So if you just type the two sides in as separate equations in Desmos, you'll be able to see where one is less than or below the other, or potentially greater than, meaning above the other, depending on what the inequality is. All right. So again, I invite any questions that you have in chat. I'm going to keep moving through, but if you do have questions, put them in there, and I'll try to answer them as we go. Okay. So let's look at a slightly more complicated one. Question 2 here. We have 2x minus 6 greater than or equal to 8x plus 12. And so I'm going to add 6 to both sides. Minus 6 plus 6 greater than equal to 8x plus 12 plus 6. 2x greater than or equal to 8x plus 18. And now I'm going to subtract 8x on both sides. We'll end up with negative 6x greater than or equal to 8x minus 8x is 0. So 18 is all that's left there. All right. So now we need to divide by negative 6 on both sides. Over here we end up with x. Over here we end up with negative 3. In this case, I've divided by a negative, so I need to switch the direction of the inequality. And so that's the key here, is remembering, if I multiply or divide by a negative, the inequality direction needs to be switched. Okay, so you can go ahead and try this one on your own, just expressing the solution. Please try it in set notation, in interval notation, and on a number line. I'll give you about a 20-second head start, and then I'll try one of them out, or I'll go ahead and do them as well, and so you can check your answers against what I'm doing. And then we'll talk about compound inequalities. All right. So my apologies here. Put that in the wrong direction. But you can check your work against this. On a number line, we're going to have a solid dot at -3, and then the arrow extending to the left in the negative direction. For a set, the solution looks very much like the solution to the equation. And with our interval, we now have a square bracket on the 3 because it is a whole number. Or it is, sorry, because it is a part of the interval. All right. Jumping back, just going to check no questions in the chat. As usual, please feel free to put questions in the chat. So I want to talk about compound inequalities. So we'll do the very last example here on your page. 2x plus 4 less than 5x minus 11 less than or equal to 4x plus 3. So when we have compound inequalities, we need to look at the inequality. Well, compound, first of all, just means there's two of them combined. So it's two inequalities combined. Both of the outside ones are in reference to the same one in the middle. When we're looking at compound inequalities, the way that we deal with it is we look at the first half of the inequality, so the first one and the second, and then we look at the second half of the inequality, so the second one and the third. We get two separate answers, and then we find the overlap of the answers. So which x values are part of both sets of answers? That's going to be the overall answer to the inequality. So let's go through and do the first one here. Just going to make sure I'm on screen. So I literally separate them out into two inequalities. All right, and now that we've had some practice, I'm going to move through pretty quickly. So I'm going to bring the 11 over here. 11 plus 4 is 15. 5x minus 2x is 3x. Divide both sides by 3. And we get, this will be x greater than 5. All right, so we would have had 5 over here that was less than x. So I've swapped it around, x greater than 5. For this one, I'm going to add 11 to both sides. That's going to make 14 over here. 5x minus 4x, that's going to make x. So we have x less than or equal to 14. And now we have two different solutions, x greater than 5, x less than or equal to 14. And this is where the number line starts to really be helpful. So there's 0, there's 5, there's 14. If I draw the first one here, I'm going to have an open circle at 5 going up forever because x is greater than 5. If I draw this second solution here, I'm going to have a closed circle at 14 and then going down less than 5 or less than 14 and down forever. And so what we're looking for here is the overlap. Where do both of these solutions have valid values? And so in this case, we can see, well, the overlap is starting here at 14 and then going down. There's 2, 2, 2, 2. And then when we get to 5, 5 is not included. 5 is the first point where only one of the two inequalities is true, right? 5 is less than or equal to 14, but 5 is not greater than 5. So this one here is our correct solution to both inequalities at the same time, and therefore the compound inequality. So therefore 5 is less than x, which is less than or equal to 14. And we can also write that as a set. And just like the other sets, if you have it as an equation, or an inequality, it's very easy to write it as a set. And we can also write it as an interval. So we have 5 as the low end. It's not part of the interval, so it's a round bracket. 14 at the high end, it is part of the interval, so it's a square bracket. All right. So those are the examples that I wanted to show you today. Take a moment, let me know in chat. Give me a 1 in chat if that's making sense. Ask me a question in chat if it's not. What do you think of this? All right. So I see we've got a couple people in the chat or on the stream. Not seeing anything in the chat. If you do have questions, please send them to me by email. Very happy to answer them for you. Hopefully that helps explain linear inequalities. Over the next few lessons, we're going to talk about inequalities in a variety of contexts. And so this is a bit of a foundation for that. So try out the questions in the homework. Let me know what you think, and we'll talk about some of the trickier kinds of inequalities in the next few days. Have a great rest of your day and a quiet weekend. Take care.